This is section 3.3, and we're going to begin making linear combinations. For number one, say you're at a bake sale, and bread costs $2 a loaf, and cakes cost $3 each. You want to buy some of both. You have to buy some of each, and you can only spend $20. Let's write an equation. You pay $2 per loaf of bread, plus $3 per cake, and you end up with $20. I'd like you to plug in some points and find out how many different combinations of breads and cakes you might buy and what they are. I'll give you a hint, there's a total of 3 combinations. Alright, let's see if we got those right. You have 3 combinations, 7 loaves, 2 cakes, 4 loaves, 4 cakes, and 1 loaf, 6 cakes. We can find those by plugging in values for B and finding the corresponding value for C. Hopefully everyone was pretty comfortable with that. For example, in this first one, when you plug in 1 for bread, you end up with 6 cakes. Now let's talk about whether or not we can graph those solutions. If we look at these, could these be configured as points? When we do this, we always put our variables in alpha order. For example, x comes before y, so bread will come before cake. And that's just an easy way of always ending up with the same graph as everybody else. So always put them in alphabetical order, your first letter being your independent variable. Now let's go ahead and graph these solutions. This would be my bread. This would be my cake. If I have 7 bread, I have 2 cakes. If I have 4 bread, I get 4 cakes. If I have 1 bread, oh my goodness, I get to have 6 cakes. And you can see there's a linear relationship here, but I don't have all the solutions. My domain is obviously 7, 4, and 1. And my range is 2, 4, and 6. All right, last example here before I give you a problem to do. Crazy chemist Chad mixes 8 ounces of a 30% solution with B ounces of a 40% solution. Final mixture contains 10 ounces of acid. Write an equation relating A, B, and the total amount of acid. Well, let's see. I have A mixtures at 30%, so I'll call that 0.3A. And I'm adding to that 40%, or 0.4 of B, and I should end up with 10 ounces of acid. Crazy Chad. All right, now we want to know how many ounces of the 40% solution must be added to 3.5 ounces of the 30% solution to get 10 ounces in the final solution. So I know 3.5 of the 30, so that's going to get plugged in here for A. And I am looking for how many ounces of the B value, or the B solution, to add so that I still get 10 in my final solution. Let's go ahead and multiply 0.3 times 0.35, and we get 1.05. Let's subtract that on both sides so that we get our B variable alone. And I get 8.95. Divide both sides by 0.4, and I get 22.375 ounces. Could you graph this situation? Absolutely. It might not be the easiest. Again, remember we would use B as X and A as X and B as Y. I would recommend either using x-intercepts and y-intercepts to graph, or clearing your decimals. All right, what I'd like you to do for tomorrow is an example like we did earlier. In hockey, a win is worth 2 points, tie is 1 point, and a loss is worth 0 points. If early in the season the Wolves had 11 points, write an equation expressing the situation. Make me a table of all possible wins and ties and losses. And losses will be 0, so you'll just have W and T on your table. And then graph the values from the table. And I will see you tomorrow.